Let's consider this example using the Nernst equation. Here we have two half reactions that I've taken from the table of standard half cell reductions, and we have their standard half cell potentials. We're given concentrations that are non-standard, so none of these are 1 molar or 1 atmosphere pressure. We want to find the cell potential under these non-standard conditions. So we would use the Nernst equation. In order to use the Nernst equation, we need to know the standard cell potential, and we need to know the balanced redox reaction, because we're going to use the reaction quotient. We need the products over reactants, so we need the balanced equation. Let's say I want to know the E non-standard for the cell running in the spontaneous direction. So that means I would want the standard cell potential to be positive. So I would reverse one of these reactions so that the standard cell potential is positive. So when I reverse one of these reactions into an oxidation, I would have to change the sign on the standard half cell potential. So if I changed the top reaction to an oxidation and left the bottom one as a reduction, I would have negative 1.33 plus 0.7. That's a negative cell potential, so that would be non-spontaneous. So if I reverse the bottom reaction and keep the top reaction as a reduction, then I would have 1.33 minus 0.7, which is positive for the standard cell potential. So I'll write this reaction in reverse. And if I write it in reverse, I've got to change the sign for the half cell potential. Okay, so now I have a reduction and an oxidation. They come balanced from the table, so I don't have to balance the reaction. All I have to do is make sure when I add them that the electrons cancel. So I have 6 electrons on the left, but only 2 on the right. So if I multiply the bottom reaction by 3, then I'll have 6 electrons on the right and the left, so my electrons will cancel. So that's going to give me 6 total electrons in the redox reaction. So that means that N is going to be 6 moles of electrons. So I'll keep that in mind when I use the Nernst equation. Okay, so now I'll add these two half reactions. So I'll get the dichromate ion plus 14 hydrogens. The electrons cancel, plus 3 hydrogen peroxides. And that will give me 2 chromium 3 pluses, 7 waters, and 3 oxygens, and 6 H pluses. The electrons have canceled. So that's my balanced redox reaction. Now one thing I'll notice, I have hydrogens, H pluses, on both the right and left side. So I'll cancel them out. So I'll subtract 6 hydrogens from the right and the left. So that means that I'll have 8 H pluses on the left total. So this is my balanced redox reaction. 6 electrons are transferred during the reaction, 6, and 3 times 2 is 6. And so now I can create the reaction quotient because I have the products and their stoichiometric coefficients, remember, powers in the reaction quotient. So that's why I needed the entire balanced redox reaction, so I know all of these coefficients so I can put them in the reaction quotient. So now I can use the Nernst equation. So remember, E cell non-standard is E standard for the cell minus RT over NF times the natural log of Q. So I'll plug numbers in. E for the cell is equal to E standard for the cell, and that's just the sum of the oxidation plus the reduction. That's going to give 0.63 volts. So I have 0.63 volts for the standard cell potential minus R, 8.314 joules per Kelvin mole. Now I'm using R in joules because I'm going to have joules divided by Coulomb, and that will give me volt to go with the volts for the cell potential. Temperature, I'll need temperature in Kelvin, so I'll change the temperature to Kelvin, 298 Kelvin, divided by N. This is the number of moles of electrons transferred in a balanced redox reaction, so that's 6. And Faraday's constant. And then I have natural log of the reaction quotient. So it's the concentration of the products divided by the reactants. So I have product, I have chromium 3 plus squared, water. Now water's in the liquid phase, it's pure liquid. So remember, I don't include liquids, pure liquids, and solids in the equilibrium constant or reaction quotient. So I'll leave water out. I have oxygen, and that's cubed. Those are my products. And the reactants are dichromate to the first power, H plus to the 8th power, and hydrogen peroxide to the 3rd power. Okay, so now I'm ready to plug numbers into my reaction quotient. So chromium 3 plus is 0.01 molar. Oxygen is 0.3 molar. Dichromate is 0.1 molar. H plus is, well, I haven't been given it, but I've been given the pH. So remember that the pH is negative log of the H plus concentration. So that means that the H plus concentration is equal to 10 to the minus pH power, just using the properties of log. You saw this in the acid-base section. So H plus is going to be 10 to the minus 4th power. 10 to the minus 4th. And hydrogen peroxide is 0.2 molar. Okay, so now I have my reaction quotient. I'm ready to plug numbers into my calculator. Okay, so all of this, when I plug it into my calculator, gives me 0.29 volts. So my standard, so my non-standard E for the cell is going to be 0.63 volts minus 0.29 volts. So that's going to give me, I'll write it here, so E for the cell is equal to 0.34 volts. So this is my final answer. The non-standard cell potential is 0.34 volts. So it has been reduced from 0.63 down to 0.34 because of these non-standard concentrations.